Okay, yeah, this specific course is concerned with the design of linkages. That's a very important branch of mechanical engineering because mechanical and I would say also mechatronics engineering, those two branches of engineering or two disciplines, deal with things that move as opposed to like civil engineering, for example, which deals with structures and things that are usually stationary things. So if we deal with machinery, that's like moving things. And the crux of the machine design is really a linkage, and that's the part of the machine which receives power or motion from a prime mover, as being an engine or an electric motor or a hydraulic cylinder or whatever, and then transforms this energy to the other end of the machine in a specific mathematically based fashion to move some other part of the machine in a calculated way type thing. And we'll learn in this course here how to design how and also to analyze a linkage and to look at the aspects which control the performance of a linkage, and we'll learn the tools which help us to conduct this like design exercise, if you like, type thing. So now uh, usually like we have I have a linkage here in front of me on the screen, and just wanted to give you some definitions, things that like the jargon, if you like, that we use in this specific field of mechanical engineering. So when we say a link is just the member of the linkage, such as this link here or that link there, or even the slider, this link here at this end, or even the ground link, which is stationary, right? Those are all members of the linkage or the mechanism. That's another name we use to refer to linkages, mechanism. And so those members, we call them links. Usually, when we analyze or design a linkage, we think of those as of constant length. So we think, okay, the length is not going to change of a link, even though it may be subject to some forces due to the fact that it does transmit power, does transmit torque, and some forces will have to be transmitted in the process. So it's like any other elastic element. Um, you like even steel, you can calculate if I give you a steel bar, I give you a force applied on the bar axially or whatever, you should be able to calculate the deflection that occurs due to this force based on the dimensions of the bar and Young's modulus, right? So there is always some deflection involved in the transmission of force, right? However, we say those deflections are really too small to consider in our course, or normally when you design a linkage, then we refer to these linkages are rigid. So the word rigid link here says that the length of the link is not going to change during the motion type thing. So here we have links, and these links are rigid type thing. Okay. Some other important aspect of a linkage is the joint. This is the device which links two members or two links together, connects two links together. Like for here, for example, here, that this is a joint. That's another joint, right? Yeah, this is also a joint, correct? And in fact, even the slider, which slides up and down, which slides left and right on inside the groove, or if you like, on the stationary link on the ground, that's also a joint, right? So this linkage in front of us, we have four joints. We have these joints here, these joints there, and this joint in the center here, and we have the sliding joint, fourth one. So the link in front of us really has four links and four joints. Four links being this link here, that's link number one, if you like, or I'm going to say one link number one, give one to reserve this for to the ground. So the ground is link number one, this link number two, link number three, and the slider is link number four. So I have in this here, I have in this arrangement in front of me, in this linkage, I have four links and four joints as well. All right, okay. So now one of the links is going to provide the motion to the rest of the linkage. And this specific link, which provides the motion to the rest of the linkage, we refer to as the crank. So normally the crank, so this one here, I would imagine this one here, I can refer to this as a crank. And this will be, if you like, keyed to a shaft of a prime mover, which is electric motor or an engine or whatever sort of thing. So that this will be the crank. So on the one side I have a crank. On the other side I have a slider here, which is like if it can be possibly the output link of this linkage. So if I have force or a part of torque and motion coming out, coming inside or into the linkage, at the crank's end, you imagine that there will be some resistance to the motion at the slider's end type thing. So that will be the output link, which will take the input torque and sort of transform this into forces, which you can use as the slider's end. We can possibly be cutting some metal, it can be part of a machine tool, or maybe just pressing some components or whatever sort of thing. Okay. All right, so we have the linkage, we have the members, which is like the links, and they are rigid, and also we have, don't forget, we have the joints. All right. Okay, that's important. Now, just another thing I possibly want to refer to at the moment is the fact that the joints we use in linkages, they are, you can see, as you can see in front of you right now, we have like rotary joints, like in this case, that's this joint here, joint number one, allows for this joint here, allows for rotational motion, right? This joint here allows for, like the crank, link number two, to rotate about its own axis. So this joint here allows for rotational motion. I'm just going to refer to this by the letter R for the moment. I have another type of joint here, which is the sliding joint, right? The sliding joint. So I'm going to refer to this with the letter P, right? Uh, because normally we refer to the joint as a prismatic joint in this branch of mechanical engineering. We say that's a prismatic joint. We use the term prismatic because we want to say the specific member here that slides inside another member is not allowed to rotate inside it. So hence, if it's not allowed to rotate, it's like a prism and sliding against another prism. So that's we sort of the similarity there more than anything, analogous to that. All right. One thing we can look at, just it's a very important thing to say at the moment is really some authors in this specific field of mechanical engineering, they say the joints are the most important members of a linkage, and the function of the link is really to maintain that like fixed geometric relationships between or among different joints. So like link number two over here gives me the fixed distance between this joint here, the fixed center, and this joint here, this end, another revolute joint here. It allows rotational motion. So link number two, which is the crank, sort of just the function of the link is just to maintain those two joints parallel to each other at a given distance from each other, that sort of thing. Now, Another thing I need to discuss at the moment is really to look more into those joints and what they do type thing. So, and what the kind of motion they allow. So let me, for a second, just insert another file here, another table. So I'm going to insert another page first, my presentation. So I'm going to insert pages, right? Okay. And now over here, I'm going to insert a table, which has, if you like, a list of joints that are available for us. So, okay. So now this table here, so that it just tells me that I have revolute joints, that's all. And these joints allow for angular motion, so that angle here, theta, if you like, is going to change. It will be allowed to change in my linkage, similar to this angle here. Can it change? The angle here, can it change? Right? And so on. And this angle here, can it change? So those angles are be allowed to change. And also the other joint I have is a prismatic joint, like the one we have over here, as I said before. So this one here is the prismatic joint. All right, okay. So now just let me say that this specific linkage, before I leave this bit here, this specific linkage, if we look at it, we'll find that every point on the linkage actually moves parallel to a specific plane, right? So all the points move parallel to a specific plane. We can project everything to a plane behind the linkage, and everything will be projected with its own proper dimension type thing. There's no angle between any link and the specific plane behind the linkage. So everything can be just projected, right? Type thing. So hence we call this a planar linkage. Right? That's a planar linkage, right? But some some linkages are more like 3D type stuff. They move in space. They come out of a plane, exactly like a human arm or a robot, right? The robot does move out of a plane. So we call in a linkage such as this one, we refer to as a spatial linkage, right? So the other type of linkage is. So that's another classification of linkages, like planar linkage and special linkage type stuff, right? So in this specific course, our focus is really the planar linkage, but we may just look at this, like spend a couple of minutes on a special like special linkage, calculating something we refer to as degrees of freedom, right? And this will be clear in a second. Now I have other joints here. Those joints are used in, by the way, those joints are used more in special linkages, more than planar linkages, because they allow the member to come out of a plane type thing. If like you see those two joints I discussed earlier, they just maintain the links inside plane or parallel to a plane, right? If we look at those other joints here, we have this joint which is called cylindrical joint, right? This cylindrical joint, imagine you have a point attached to this link. Cylindrical joints allows the link to slide, right? Up and down inside that, but also allows the link to rotate. Sliding remains inside on as in a specific plane. But once it rotates, right, with an angle theta, then it comes out of a plane. And hence, the cylindrical joint really is more like uh, special type joint, using special things. The other joint which is used more in special things is a spherical joint. Like we call this ball and socket joint, right? That's another name. The ball and socket joint, right? And this joint here allows, imagine this member here can rotate about the center line. Once it rotates about its own center line, it will come out of a plane. So imagine a point on, if this was like, this was like a bar, rotary bar or whatever, and there is a point on this like a cylinder here, and once it rotates about the axis and the center line of center line of this member, this point will come out of a plane 100%. So that's again that's a special effect. So it will leave the so no, normally ball and socket used in special linkages, and but this point itself, this joint itself allows for three different motions, as opposed like the cylindrical joint allows for two motions, for sliding and for rotation, theta, sliding S and rotation theta. But the ball and socket allows for three different angular movements, if you like. We can call them alpha, beta, gamma. So this joint allows for three movements. That's why we refer to this joint as a 3 degree of freedom joint, if you like. Uh, the cylindrical joint is a 2 degree of freedom one, because going to say 2 degree of freedom joint. This one is a 3 degree of freedom joint. Why 2 degree of freedom? Because the cylindrical joint allows for sliding independent from the rotational motion theta. So you can just fix S, no sliding, and you can rotate theta, and you can fix theta, so the thing doesn't rotate and you can slide. There are two independent things allowed by the cylindrical one. And now the prismatic one is only a single degree of freedom one, right? So that's single degree of freedom joint. It allows only this one freedom, which is S, right? And the revolute one also is a single degree of freedom joint. It allows for the single motion, which is theta. Okay. Now, all right. So now, just start to talk a little bit about degrees of freedom. So, what is degrees of freedom? I sort of mentioned briefly in here. So, we say just let's talk a bit about the degree of freedom, because this is an important thing which is related to the mobility of the linkage. So you can design a linkage. If you don't understand the concept of degree of freedom, you can design it, spend lots of time and lots of money designing and calculating and manufacturing, and then after that, when you put it together, it doesn't actually move, because you don't understand the concept of degree of freedom. So when you know it's a degree of freedom is a tool that you can utilize to your own benefit when you design a linkage. At least you know exactly uh, how, if it was going to move or not. You can also tell by degrees of freedom as to whether, like, how many motors you need to drive the linkage, how many prime movers you need. So if we say if that's a single degree of freedom linkage, this means you need only one motor to drive it. If it's two, you need two motors attached to the linkage and run independently to drive the linkage, and so on. So hence, the concept of degree of freedom is very important. So also, the meaning of degree of freedom as well, not just the prime mover, how many prime movers you need, how many motors you need, I mean, but also it is how many parameters you need to describe the position of any point in the linkage. Like if it's single degree of freedom linkage, you need one parameter. Let's say will be the angle, for example, of the input link. So once if I give you the angle of the input link, you'll be able to calculate where every point is located in the plane at this specific point in time. I think sort of thing. So that's the degree of freedom has a mathematical connotation Also, it has a physical and design connotation as well. So now let's look at the concept of degree of freedom and how it is calculated. So now I'll just start. So let's write here degrees of freedom. So I'm just looking now in the plane, right? So I have X and Y plane. If I have a line in a plane, right? So this line in a plane, how many degrees of freedom does it have? Now, a point in a plane, point has can move up and down to any value of y, can move sideways to any value of x. So it has 2 degrees of freedom, being x and y, right? The point has 2 degrees of freedom. How about a line now? So if the point develops into a line. So in this case, we need 3 pieces of information to draw the line. We need x, y of a point, and also we need the angle of the line. So a line is really a member of a linkage, of a planar linkage, because the line connects the joints. So in linkage analysis, we don't really worry much about the actual shape of the link. We just what we're interested in is the distance from one joint to another, which is a line. So the line replaces the link type thing, right, irrespective of the shape. So now this is a link here in the linkage, and or now at this point in time, it's just floating in a plane, and it has 3 degrees of freedom, being x, y of a point, and the angle theta. Now, the length is constant because length to any point doesn't change. So it's not a degree of freedom. It doesn't vary. If it doesn't vary, it's not a degree of freedom. Once we know the value, we know the value type thing. But things that can vary here, the length can float to any x, y, and can take any angle theta. So hence we say that's a 3 degree of freedom arrangement here, right? Now, if I have two links, so if I have right, if I have two links here, so every link has 3 degrees of freedom, right? So this one has 3 degrees of freedom plus 3 degrees of freedom. So the total is 6 degrees of freedom, which makes sense, correct? I mean, degree of freedom, I can say degree of freedom is n times 3, where n is the number of links. It makes sense, just simple, really arithmetic more than anything. All right, so now if I have the two lines now constrained by a revolute joint. So now I have line number one, line number two, and there is a joint which connects the two lines together. So now how many degrees of freedom do I have in this case, right? I used to have 6 before when I added with two lines floating independently. Now adding constraints like constraining the movement by a revolute joint, right? So revolute joint, right? This adds constraints. So how many degrees of freedom do I have at the moment? So this line here has 3 degrees of freedom, being x and y of any point, right? And an angle theta, right? Let's call it theta 1, all right? So that's 3 degrees of freedom. But now, to get the second line, I just need the angle between the two lines. Okay, because once from the first line, I can find the x and y of any the point on line 2, right? So if this was line 1, this is line 2, right? This point R gives me x and y of line 2 already because it falls on line 1 and I know everything in relation to line 1. So the only thing I need to find line 2 is find theta 2, which relates line 1 to line 2. So now degrees of freedom here is equal to 4. Okay, being what? Being xy, theta 1, theta 2. Okay, meaning that they are joint sort of deducted 2 from the previously calculated value, which was 6 before. So now 6, now it's 4. Makes sense to me because R allows 1 degree of freedom. So if in the plane I have 3 degrees of freedom, 3 possible degrees of freedom, R will have to constrain 2 because it allows only 1, which is angle theta, right? So I can write my equation now saying that, well, F is equal to 3n minus 2r. Okay, we can prove this a little bit more. Like it's here, I have 3 times 2 minus 2 times 1, correct? And this is 4. Now I can add another revolute joint. R, another R, and I can say degrees of freedom here, x, y, right? And this angle here, theta 1, theta 2, theta 3. So degrees of freedom now is equal to 5. So degree of freedom is equal to 5, correct? So my equation now is going to work nicely. I'm going to say F 3n minus 2r, and so it's 3 times 3 minus 2 times 2, and that's 5. Okay, so that's magnificent. All right, so now what if I give you a linkage to do such as this one now? So if I say I give you an example and I say I have this linkage, let's calculate degrees of freedom, right? Find degree of freedom, right? So what we do is we count our links. So start counting links. Let's do this together. I start by counting the stationary link as link number 1. Right, so that's link number 1, right? And then I have link number 2, link number 3, link number 4. I always try to put circles around the link number. So that's something I always want to do. Now I have revolute joints here, another revolute joint here, another revolute joint here, another revolute joint here. All right, okay. So now if I say, now let's calculate F, degrees of freedom F. So I'm going to use a different color here. So go say I have N is equal to 4 links. My revolute joint is equal to 4 revolute joints. Correct? Okay. So now F is equal to, let's apply the equation, which says 3N minus 2R. I can say 3 times 4 minus 2 times 4, which gives me 8. So that's 12 minus 8, gives me 4. So now this linkage here, does it have 4 degrees of freedom? This is a question I ask you. I want you to think about it. for a second now. Does this linkage have 4 degrees of freedom? In other words, do you think I need 4 motors to drive this linkage at all? Do you think I need 4 motors to drive this linkage or just one motor, right? Okay, so, well, I tell you now, and it makes sense, this linkage has a single degree of freedom. You only need one motor to drive it. You don't need 4. So this means my equation needs to be modified. It doesn't encompass every aspect I have in the linkage, right? So where did I go wrong with my calculations here? Type thing. All right. Let's see what happened here. Take stock. I had, I said I had 4 links, and I do, that's not a problem. And 4 revolute joints, and I do, that's not a problem. Okay. Here, when I said 3 times in, this means I accounted 3 degrees of freedom for each link I have, correct? Minus 2 times R, because I know every revolute joint deducts the freedom by 2 because it allows only one angular freedom type thing. So this makes sense to me. You know where I went wrong is when I said 3 times n, because I assumed all 4 links can move, right? I assumed all 4 links have 3 degrees of freedom. I didn't take into account that I have a link which is a stationary link, right? We refer to this as a ground. So every mechanism should have a ground. Now, this ground does not actually move. So the freedom degree of freedom for the ground is equal to 0 because it does not move. So I gave it when I multiplied by 3 here, so I accounted that 3 degrees of freedom for the ground. So what I need to do is to go out back and deduct the ground from my calculations. So I need to say 3 n, but take away the ground from n. So you counted with the counting, you counted because there's a convention, because it's a link, should be counted, but then it should be deducted from the equation of a mobility or degrees of freedom. All right, we'll refer to this also as mobility. So that's minus r. So now I have a more accurate equation at the moment, because now when I say, let's apply now this equation, f is equal 3, 4 minus 1 minus 2 times 4, and this gives me 1. All right, so now this linkage is a single degree of freedom linkage. That's right, single degree of freedom linkage. 1 motor is needed to drive it, right? So 1 motor is needed to drive it. Where to fit the motor? We'll talk about this later on. We'll fit the motor at the link which we think is going to do 360. So when we design the linkage, we make sure one of the links will do 360, and then we attach a motor to this link if it's continuous motion motor as opposed to a servo motor or something, right? That's one thing. But also we can describe the position of any point on the linkage if we knew one parameter, and normally this one parameter usually would be the angle made with the x-axis by the link which is going to do 360, which we refer to this link as the crank, because normally you attach the crank to a motor. The motor has a constant velocity omega, like radians per second, right, type thing. So simply we can say the angle at any point in time of this link is known because we know the velocity and we know it's constant. So then, right, so this angle theta, we can calculate the position of any point in the linkage with the knowledge of this angle theta. And I can give you an example straight away right now. So I'm going to say, I'm going to put some numbers here, like page numbers. I would say it's 1, 2, 3, page number 4. Right. So I'm going to prove to you that for the 4-body chain, I need the knowledge of only like one angle to calculate any other point or find any other point in a plane. So if I have a 4-body chain, such as the one looked at above, and then, right, so I'm going to say now point A, point B. So, right, I know this link is going to do 360, and this link is going, or will move on a circular arc, right? So, because rigid, this link is going to move on a circular arc. Graphically, I'm going to prove it has a single degree of freedom. So let's say I tell you that this linkage, this link here, the angle of this link has is now whatever value, let's say 60 or 70 degrees or something like that. So point A has moved to position A prime. Find the rest of the linkage where every point else has gone as a result of that. So now this exactly means I'm giving you one angle here, and that's exactly what it means. And then I'm saying find the list of the rest of the linkage. So if you want to find point B prime, you know B is going to move on a circular arc, correct? And then if this link here is number, so if this is R1, because link number 1 is my ground, link, I'm going to call this link number 2, this link number 3, let's say this length is R3, this length is R4, right? So this link number 4, this link, this length of that is R2, constant length R2. All right. So now I want to find where point B prime has gone. So to find it, what we do is we compass with the compass, we place the compass here, and then we open, then we'll draw a like circular arc with the radius R3, correct? And then this is going to intersect the radius R4, right? At a point, this is going to be point B prime, right? So now this length here is R3, and I just connect those 2 points. That's R4 again. So this is a new position of the linkage, right? This is a new position of the linkage. Just based one thing, like one piece of information was given, which was this angle here, right? Let's say I'm just like graphically can assume any value for this angle. So that's a single degree of freedom linkage, just to highlight or prove the value we got previously. All right, so okay, now we know the equation. This equation it does work. It's a good one. Now, what if we have, because my linkage here had also a sliding joint, prismatic type joint, right? Sort of thing. So I need to include this also in my equation. So I need to improve the equation a bit by adding the effect of the sliding joint. Now I want you to think, how will a sliding or prismatic joint be added in my degree of freedom equation? All right. So again, if I go back to the same analysis I did before, so just insert a couple of pages. So this was page 5, page 6, page 7. All right, okay. So now if we go back and try to see the effect of the prismatic joint on the thing. So again, I'm going to say I have my plane, I have a link and another link, and they are attached together with a sliding. Rotation is not allowed. So this here a prismatic joint, prismatic, right? So the freedom I have, which this allows, is the motion s. Can move up and down. This motion distance is, right? But that's all prismatic. So there's no, this is not allowed. Rotation is not allowed, right? Okay. So if rotation is not allowed, then what I'm dealing with is just a prismatic joint. Then how many degrees of freedom do I have in this case? I have this link here. This, I'll say, okay, this link here has 3 degrees of freedom, x, y, and the angle theta, right? And then I have to find any point on the other link. I need to know the distance because the angle between them is fixed, right? So I need to know S. So degrees of freedom here, degrees of freedom here equal to x, y, theta, and S equal to 4. Right. So this tells me that IE P, right, deducts also 2 degrees of freedom, because without it would have 6, because I have two lines. So that line 1 and line 2. So they should have 6 degrees of freedom independently if they were not constrained together by a joint, but they are. Okay. So now I have, and then this joint sort of managed to reduce the freedom from 6 to 2 to 4, then it can deduct actually 2, similar to P. So now I can go back and say degrees of freedom 3n minus 1 minus 2r minus 2p. All right. So which takes me to this other new example. What if I have a linkage that's something like that? How many degrees of freedom do I have? So I say, okay, again, find degrees of freedom. Let's count our links. So all the fixed points together, all of them together, that's one link. Then that's number 2, link number 3, link number 4. So the slider is a link. Don't forget, slider is a link. All right. So that's a link. Right. How about the joints we have in this linkage? I have this joint allows the angular thing to happen. That's R. Another R, because this angle changes. If the angle changes, that's an R. And also here, because this angle changes, that's an R. And this one here is prismatic. That's sliding. So I have n is equal to 4, revolute joint was equal to 3, and prismatic is equal to 1. When I apply my equation, I go F is 3, n minus 1 minus 2 times R minus 2 times P, right? I have n 3 4 minus 1, which is 2 times 3 minus 2 times 1. So that's 1. So it's a single degree of freedom. So that's single degree of freedom linkage as well. Now, and you can prove it. So you need one motor to drive it. And also, if I give you the angle of link number 2, for example, you can find the rest of the linkage. You can draw it. No problem at all. Because if I give you the angle of link number 2, so link number 2 is going to move in a circular arc. If I say this angle here of link number 2 is what, like 50 degrees or something like that, find the rest of the linkage. So you know, with the compass here, you draw link R3, right, from here to there, and this will find you a slider. So you have done it. You can draw the linkage at any position of the crank if this position is given. So that's one piece of information. Hence, it's a single degree of freedom linkage. And also the motor out. If I had a motor just connected to the crank axis here, and the motor will be sufficient to drive the linkage to whatever position I wanted to go to. All right. Now, what we do? Like, let's do another one, a little bit more involved than this. So if we have, okay, maybe I can do the other one here. So if I have a linkage such as this one, here, and I want you to calculate the degrees of freedom of this linkage. Right now, as usual, what we do, we start counting our links, right? So all the fixed links, all of them are 1. So they are, we call them 1. That's all the stationary links. Like this end, that end, that end, all of them, we think they fall on the one link number 1. Irrespective if they are attached on the drawing or not, does not make any difference. Okay. And now I have link number 2. I can take this as link number 2. And then I have link number 3, which is a slider. Right? Slider is a link. Again, because I've noticed people always forget that. And link number 4, this link number 5, link number 6 is the other slider. So my links here, n is equal to 6 links, correct? How many revolute joints have I got in here? So every time I have an angular change, that's a revolute joint. So let's change the color a bit and say that's R. This one is a revolute joint. This one is a revolute joint here, 100%, because the angle will change. And that's a revolute joint. And this one is a revolute joint. 1, 2, 3, 4, 5, 5 revolute joints. How many prismatic joints? I have one prismatic joint here and one prismatic joint here. So that's 2. So if I apply my equation now, I go F is equal to 3, 6 minus 1, 15, minus 2 times 5 gives me 10, minus 2 times 2, so this will be equal to 1. So I have a single degree of freedom again. So that's single degree of freedom linkage. All right. Now, sometimes we have an interesting situation where one of the links, like we have things like that, they're like contact that occurs on the outside of a link. For example, if I have something like this, so if I have, let's say, that and that, right? So that's this here we refer to this as a cam, right? And we'll call this the follower. So that's follows the motion of the cam, right? That's a problem. That's linkage, right? And the contact here just occurs on, that's an interesting contact I'm talking about. We know in this case, this here is the normal R, the joint. This here is prismatic. I'm not going to allow rotation here in my design. That's prismatic. Now, what about this one? We haven't seen this one before. All right. And now let me introduce that. So we have the joints we looked at previously, like all the joints we looked at the revolute joints, right? I'm going to go back quickly here. Revolute joints and a prismatic joint in terms of the planar situation, right? Things in a plane, right? In the spatial, we looked at cylindrical joint and ball and socket joint in terms of spatial things. All those joints, in fact, when you look at them, they feature surface contact, surface to surface contact. So even the revolute joint is more like a pin, right? That's a pin inside something like, like a bearing of some sort, like a bushing or something like that. So that's surface on a surface. Sliding or prismatic is the same, surface on a surface, right? So all of those are surface to surface contacts, right? So now, however, this other one, and I looked at now, just not surface to surface, because normally the contact here can occur on in a plane like that. We can say a point in reality can be a straight line. So that's a point or a straight line contact. Normally occurs on the outside of things. So a point or a straight line contact has a different, like, all right, so like there is the way we deal with it will be obvious very soon. But let me say there is part of the jargon we use in the linkage analysis. We say the joint is either a lower pair or a higher pair. So we refer to a joint by the word pair because it actually pairs two links together, right? So if it was a lower pair, this means that we have a surface to surface contact. So all the things we looked at are lower pairs. So we have lower pairs and we have higher pairs. So higher pairs when we have point or line contact. This is surface to surface contact. Right. So this here is a higher pair. Okay. So we have our lower pairs, the common ones like R for revolute, P for prismatic. Okay. And that's for like in the plane and special ones will have like ball and socket and we have cylindrical. But also we have that all those who lower pairs also have the higher pairs, which higher pairs occur when you have a cam with a follower such as this one, or two gears meshing together because they touch each other on a line, for example, or a point contact, if like theoretically speaking. So that's really we call them higher pair. So higher pair does affect or should be considered in our degrees of freedom equation, and that's how we think about it. All right, if I have, let's just reason with that. So if I have two links, so over here, so I have link number one and link number two attached with a higher pair, right? Higher pair H, right? How many degrees of freedom do I have? So, all right, let's think about it. Now I have it's an easy one to consider, by the way. So I have over here, I have X and Y of a point, and the angle that's 3 degrees of freedom. Higher pair allows this to slide and allows this to rotate. You see what I mean? So it actually together we have 5 degrees of freedom. So I have 5 degrees of freedom, being x, y, theta 1, s, theta 2. So the higher pair deducts 1 degree of freedom, because without the higher pair would have 6, like 2 links. Every link has 3. They are free, both free to move. So this means the higher pair deducts 1 degree of freedom. So instead of, as opposed to P, which deducts 2, and R deducts 2. So the equation now, F is equal to 3n minus 1 minus 2r minus 2p minus h. This is the degree of freedom equation in a plane and taking into account higher pair. So if I go back to my example there and try to solve it, so now I have the cam, I have follower here, and the cam, and that's an higher pair. I have R, I have prismatic P. Right, let's count the number of links. So link 1 is all the frame, all constant, fixed, stationary links, that's 1. Uh, I have 2 being the cam, I have 3 being the follower. So n is equal to 3, prismatic is equal to 1, revolute is equal to 1, h is equal to 1. Correct? So my freedom then will be equal to degrees of freedom. F is equal to 3, 3 minus 1 minus 2 times 1 for R, 2 times 1 for P minus H, 1 times 1 for H, right? So that this will give me at 6 minus 5, so single degree of freedom, right? Which means if I need one motor to fix here, right? One motor, or if I give you the angle theta, you should be able to calculate the motion y just with the knowledge of this single degree of freedom, which is angle theta. So another example here I'm going to look at is, so that's another example. I'm going to say I have a roller, I have a cam, and right, so that's how many degrees of freedom we have in here. That's another famous cam follower linkage. The difference between this one and the one above it, this one we call it flat phased follower. Flat phased follower. This one here is a roller follower, right? So that's roller follower, roller follower. All right. So how many links we have here? So again, let's count our links. So I have 1 for all the fixed links. I have 2, I have 3, I have 4. So n is equal to 4. But let's look at our revolute joints. That's a revolute joint. That's a revolute joint here. 2 revolute joints, prismatic and higher pair. Right? So revolute was 2, prismatic was 1, higher pair is 1. So freedom is equal to 3, 4 minus 1, that's 9, minus 2 times 2 r minus 2 times 1 minus 1 times 1. So this will be equal to 2. So that's 9 minus 4 and 4 minus would be 5 and then minus 3. Exactly, that's 2. So 2 degrees of freedom. So does this mean here I have I need two motors to run this linkage? Of course it doesn't, because I need only one motor to run that. However, only one motor is needed. Let me take a note here, like write something to say, however, we know that only one motor is needed to drive the linkage. I mean, that's, so now why two then? The number two we're getting here, we can look at it as we have one real degree of freedom, right? Which is the motion center point here. That's the motion about the center point. But also have another freedom being the motion of the roller. The roller can rotate at any point in time. You can fix everything. So everything becomes stationary and then start spinning the motor about on axis and will be able to spin because it's round. Okay. So now this is an extraneous degree of freedom that is not doesn't affect anything. So a redundant freedom. So those two degree of freedom will have one real, one real freedom and one extraneous, if you like, freedom. This is the roller movement. All right, so okay. So that's an interesting result, and it doesn't happen often, but you'll see sometimes when you get two, you think I need two motors, but then you need to think more in depth about it. So this tells me that the results I get from the equation are useful, will be extremely useful for design, as we discover later on. But sometimes we don't take mathematics just follow the mathematical number that we get. We have to think as engineers about our results and scrutinize this result and think about the common sense. And it, not every if we don't have everything matching and running together nicely, we need to think 3 4 times about the problem before we make a decision. And that's one of the examples. And we'll see more examples in the next lecture. So I'll leave this here, and then in the next lecture I'll have more things to talk about in terms of degrees of freedom, and possibly with a bit of luck we'll start talking about geometry of for body chain and other things as well. So good luck and try to do as many examples as possible. Look at the tutorials, and if you get stuck with anything, please drop us a line on Moodle and we can talk about it. And I'm happy to answer any questions later on. Okay, bye for now and good luck.